Now we will discuss the power flow diagram of the induction motor. So what information does the power flow diagram give? It will give you the information about the input power, output power and the various losses in between. Okay, at what point they will occur. So first, what will be the input power? The input power is going to be the electrical input that you give to the stator winding. Electrical power given to stator winding. Okay, so from here the first kind of losses that you will see is the stator copper losses and the core losses. Okay, so this you can write as stator copper loss, that means the losses due to the stator resistance, and this is the stator core losses. Now what will be left out? This much amount of power, let's say it is left out. Okay, so if you subtract from the input power, if you subtract the stator copper loss and the stator core loss, then the power that is available here is called as the air gap power. Okay, so we represent it either as PG or PAG. Okay, so in different textbooks you can see different notations. This is called as the air gap power. So after this, what are the losses that you will see? Similar to stator copper loss and stator core loss, you are going to have the rotor copper loss and the rotor core loss. Okay. Now the remaining power is this much. Okay, so this remaining power that you have after the rotor copper and core losses are subtracted from the air gap power, you will be left out with the power that is available for actual electromagnetic conversion. So now, is this the final output power? No, not yet. There are some more losses to be accounted for. So what are those losses? You have the rotational losses. One is the friction and windage loss. Friction plus windage loss. Frictional losses occur whenever there are moving parts. And what is windage loss? This is because of the air resistance. The air will also offer some resistance. Okay, and after that there will be left out some stray losses. That means all of the miscellaneous losses. And the remaining power that is there, this is what is the actual output power that you are going to get. Okay, P output. So what will be this energy? It will be in the form of mechanical energy. In terms of the torque, you can write it as T output torque into the speed, angular rotation. Okay, and similarly P converted, it you can write as the T induced. Induced torque is different from the output torque. When you take away these losses, if these losses are 0, then the induced torque will be equal to the actual output torque. Otherwise, both will be different. Okay, into the angular speed. This will give you the converted power, and this is the actual output power that is available. You can write down these losses are called as rotational losses. Now, a few more important things that you need to know here is the rotor conductors have current flowing through them. Okay, but we are not getting any electrical output. That is because they are shorted. The rotor conductors are shorted. So there is no electrical output that is available. Whatever energy they consume in terms of the rotor resistance, that will appear as the rotor copper losses. Okay, so this is one point that you need to know. So you can write down rotor conductors are shorted, so no electrical output is present in the induction motor. Another important point is with regards to the core losses. The stator core losses is much higher as compared to the rotor core losses. This is because under normal operation the slip is very less, right? And when slip is less, what will happen to the rotor frequency? We know that Fr is equal to, because Fr, the rotor frequency, is equal to S times Fe, and at normal operation S is very small, because the speed will be nearly synchronous speed. It will not be equal to synchronous speed, but it is nearly equal to the synchronous speed. Then what will happen? The frequency, the rotor frequency, is actually very small, and the core losses, they depend heavily on the frequency. So for that reason, since the rotor frequency is very less, the rotor core losses will be much less in comparison to the stator core losses. So you can write, so Fr is very small compared to the stator frequency, which is Fe. Okay, since core losses are dependent on frequency, the rotor core losses are often considered negligible. Okay, so these are a few points that you need to remember with respect to the power flow diagram. So now that we have seen the power flow diagram, we will see the expressions for each of the terms. First we will start with the stator copper losses. So this let us represent as PSCU. Okay, stator copper losses. So this is what the resistance of the winding is R1, and the current flowing through the stator winding is I1. So the copper losses in this case will be I1 square R1, but this is only per phase. Okay, there will be 3 phases, so you're going to get 3 I1 square R1. So you can write down here, since 3 phases are there. This is the expression for stator copper losses. Next, what about stator core losses? So the core loss component is RC, right? If you remember the equivalent circuit, you have the shunt parameter RC here. Okay, so rest of the parameters are, this is JXM, R1, JX1, and here you have R2 dash by S and JX2 dash. Now the voltage E1 will be here. This is also equal to E2 dash, and this current is I2 dash. In fact, this is R2 dash and JX2 dash, because we are referring on to the stator side, and the current is I1. So now what will be the core loss? Since this is the core loss component, the losses occurred across this RC, that is the core loss. Okay, so the voltage occurring across it is E1. So you can write stator core losses is equal to 3 times E1 square divided by RC. The rotor core losses, since they are negligible, this we can take as the entire core losses. Okay. Next, what do we have? The air gap power. So this is PG. You can take PAG as well. Okay. So PG is equal to the power that is left out in the input power after these losses are removed. Okay. So P input minus P stator copper losses minus P core losses. You can write here, or P core, since rotor core losses are negligible. Okay. Now this is one expression for air gap power, but from the circuit, if you can see, from the equivalent circuit, the stator side ends here. This is the rotor side. The parameters R2 dash by S and X2 dash. Okay. Now air gap power is a real power. So where can we take it? The power that is absorbed by R2 dash by S. Okay. So you can also write Pg is equal to the current flowing through it I2 dash square into R2 dash by S. And also this is only one phase. So for the three phases together you will have 3I2 dash square R2 dash by S. Okay. So this we got from the circuit diagram. This is the second expression for air gap power. Now after air gap power, what do we have? We have the rotor copper losses. So we will write this as PRCU. Okay. So what will this be? The actual resistance of the rotor winding is simply R2. And what is the current? The actual current flowing through the rotor windings? It is I2, not I2 dash, remember. So I2 square into R2 will give you the per phase copper losses. 3I2 square R2 will give you the total copper losses. So this you can take as one equation. So we will change the numbering of the equations, because here you have the first equation is this. Okay. This is the second equation that we have. This is third equation, fourth equation, and this is the fifth equation. Okay. Now we can also see that in terms of I2 dash and R2 dash, if you want to represent, then what will happen? Remember that you don't have to do too much of calculation here. The resistance and the current and the voltages, when referred to the other side, they will change, but the power will not change. Okay. In fact, you can verify it. I2 dash is nothing but N2 by N1 into I2, and R2 dash is N1 by N2 whole square into R2. So what is I2 square R2 or 3I2 square R2? In terms of I2 dash and R2 dash, you're going to get 3 times N1 by N2 whole square into I2 dash into N2 by N1 whole square into R2 dash. So all of these N1, N2 will get cancelled. You're going to get 3 times I2 dash R2 dash. Okay. So you can write this equation as well. The rotor copper losses can represent as 3I2 dash whole square into R2 dash. Okay. So this you can take as equation 6. Okay. Now you can also represent the rotor copper losses in terms of the air gap power. If you see equation 4 and equation 6, what is the only term that is present extra in PG? This S term. Okay. 3I2 dash square R2 dash is nothing but the rotor copper losses. So you can write from equation 4 and 6. You're going to get PRCU is equal to S times PG. The rotor copper losses is S times the air gap power. This you can take as equation 7. What is the next term that we have in the power flow diagram? It is the power that is available for conversion from electrical to mechanical form. You can write here power converted from electrical to mechanical form. In some textbooks, this is also called as the developed power. Okay, both mean one and the same thing. So what will this be? Whatever air gap power that is available, if you subtract the rotor copper losses, then you're going to get the power that is available for conversion. Okay, so P converted is equal to air gap power minus the rotor copper losses. But we know that rotor copper losses, it can be expressed as S times PG from equation 7. So here you can write this is equal to 1 minus S times PG. So this is one equation. P converted is equal to 1 minus S times PG. This you can take as equation 8. Further, if you want to express in terms of the current and resistance, the rotor current and resistance, then what will it be? P converted is equal to 1 minus S times, what is PG? 3 times I2 dash whole square into R2 dash divided by S. Okay. So here you can write, therefore P converted is equal to 1 minus S by S times 3 I2 dash whole square into R2 dash. Okay. So this is equation 9. Finally, after the converted power, what else is left out? The output power, the actual output power. Actual output, P out, is equal to, what will it be? From the whatever energy is converted into mechanical form, from that energy you have to subtract the rotational losses. The rotational losses consist of the friction and windage losses as well as stray losses, right? So this is the expression for the output power. You can take it as equation 10. Next we will see how we can separate the rotor copper losses from the power that is available for conversion, okay, in the equivalent circuit. So separating rotor copper losses from power that is available for conversion. What was the equivalent circuit? We have R1, JX1, the core loss component, magnetizing reactance. This is the stator side, and on the rotor side we are going to have R2 dash by S and JX2 dash. Okay. Now what did we see? The air gap power, this was the power that is dissipated in this resistor. Okay. So we have 3 I2 dash whole square into R2 dash by S. You can write down here power dissipated in resistor of value R2 dash by S. Remember, there is no actual resistor whose value is this. This is just how we are representing whatever the induction motor is behaving like. Okay. So this is the air gap power. Now what is the power that is available for conversion? We have to subtract the rotor copper losses from the air gap power. So what will be the rotor copper losses? PRCU, we have seen this is equal to S times PG, or the power that is dissipated actually in the resistor. Okay. So this is 3 I2 dash whole square into R2 dash. Power dissipated in resistor R2 dash. Now what is the power that is available for conversion? This is equal to PG minus the rotor copper losses, which we got as 1 minus S times by S 3 times I2 dash whole square into R2 dash. Now what can we call this as? This is the power dissipated in a resistor of value R2 dash into 1 minus S by S. So if we want to separate the rotor copper losses from the converted power, we should be able to get R2 dash and R2 dash into 1 minus S by S in the circuit. Okay. So how can we get that? On the stator side there will be no change. R1, JX1, RC and JXM. Now on this side what we can do is, first you place R2 dash, JX2 dash. Okay. Now we want the total resistance as R2 dash by S. Okay. And we have placed only R2 dash as of now. What else should we place? This is equal to R2 dash by S minus R2 dash. Okay, this is nothing but this term, R2 dash into 1 minus S by S. Okay, so you're going to get here a resistor. This is now the variable resistor, R2 dash into 1 minus S by S. So this is now the rotor copper losses. This represents the rotor copper losses and this represents the converted power. Okay, so this is how you separate both of them.